Sadegh Riazi, co-founder and CEO of CipherMode Labs. Welcome to the Data Exchange Podcast.
Thank you, Ben, for having me.
And full disclosure to our audience, I am an angel investor to CipherMode Labs, but I will ask questions on behalf of the audience. So I'll be very objective here. All right, so let's start off with the open source project, this interesting open source project that you folks released called CiperCore. And the tagline on the GitHub repo is user-friendly, secure computation engine based on secure multi-party computation. So mouthful there. All right, so first off, what is it? What is CiperCore?
Awesome. Yeah, happy to talk about it. We open sourced CiperCore about 2 months ago, and the main thing that it does is that it allows you to create applications that can process encrypted data without decrypting it first, which is kind of like a new concept when you think about it. It essentially would open a lot of doors for people in either data science or other areas where you constantly need to access new data, and data that may not necessarily be held by you, it may be held by other people. So now the question is that how can you access that? And we think that one fundamental solution is that every computation should take place over encrypted data. If you can realize that, it essentially means that any individual can really donate their healthcare and biodata to all kinds of companies without violating their own privacy. So they can be rest assured that data remains encrypted at all times, and yet other companies and other data scientists can start doing analysis on top of it and create new AI models. So now, how can we do this? Actually, there's a field within cryptography which is called secure multi-party computation. And
for our audience, this is actually I've had a few guests on this topic over the years, and it's a challenging problem.
It's a very challenging.
There's many approaches, and so Sadegh is about to describe one of the key approaches.
Right. Essentially, when you want to process encrypted data in a fundamentally secure way, there are only two ways within cryptography that can allow you to do that. One is homomorphic encryption, which is not a technology that we're using. And then the second one is secure multi-party computation. And we believe that SMPC, in short, is much closer to being adopted by industry than homomorphic encryption.
So before you describe what secure multi-party computation is, so at a high level, right now, what is practical as far as computation over encrypted data? Is it basic averages? Take the median? So how advanced are the computations that are practical today?
No, even today we can train AI models, we can do inference, we can run analytics. There's a wide range of applications that we can support today. And that was one of the main design principles behind CipherCore. So the way we have designed it is that you can start writing your own programs in programming languages like Rust, Python, C++, without requiring any knowledge in cryptography. And then we would be able
but can I write my programs using the libraries I like and are familiar with?
Yeah, I mean, that's the whole point. Well, I need to break it down. So today, you need to use CipherCore APIs. That's how it works. So if you want to do matrix multiplication, if you want to train an AI model, you need to use CipherCore APIs. What we want to do, which is our major next step, is that we want to support any standard AI framework, like PyTorch and TensorFlow. And when we get there, which we will be there in like a few months, then you can use their APIs, PyTorch and TensorFlow APIs, without code modification, and you can run it over encrypted data, which is a major challenging task. And the value has been clear to many people. How to do it was not clear, and that's exactly what we are building.
So from a developer experience, I would a few months from now, once you have this integration with PyTorch and TensorFlow, I can take a PyTorch program I already have, and then now point it to encrypted data and maybe make some a few modifications, and it's good to go.
Exactly, like minimum modifications. Like what we have in mind would be something literally as simple as just like importing CipherMode, and then you're good to go. You can use PyTorch APIs. You don't need to learn any new set of APIs.
I see. So then, but for now, you're saying that's still in the works.
Yes, but we have figured out all the pieces that we need to build in order to realize that, which is a major advancement compared to before. So before, the reason, actually, one of the main reasons that secure computation or secure multi-party computation has not been used at large scale to date is that it's very challenging to use it. The protocols came around decades ago, but now we are still talking about like development, deployment, integration. So CipherCore is removing that big complexity. It's basically, as a software engineer, as a data scientist, maybe people are not interested to learn cryptography, but at the same time, they should be able to benefit from secure computation.
So there are other startups that use homomorphic encryption, but then when you kind of drill down and look at it in detail, they can maybe do very basic models like regression, if that, and then training is not practical. Inference is kind of still slow and batch. So what's your guys' goal in terms of long term, in terms of first of all, the types of models, and two, can it do training and inference, and is the inference practical enough to be deployed?
Yeah, very good question. So first of all, just as a rule of thumb, we are 2 to 3 orders of magnitude faster than homomorphic encryption. So it's essentially, it could be a difference between like day and night. It's important to realize that because we also have computational overhead, obviously, compared to if you were able to train a model over plain text data. But right now, the overhead, we believe, is within the range of possibility. Like if it takes 1 hour for you to train an AI model, and now you want to access more data, but you can't, then that's the end of it. Like that's basically the end of progress. And now we come in and we say that you have a trade-off. You can have more computation time. It takes longer. It's a little bit more expensive, but it's doable. Like instead of going through a lot of legal contracts to make sure how data is stored, who governs it, who owns it, and what are the risks around it, which would take forever to identify, we say that use CipherMode, run it over encrypted data. Yes, it takes longer, but you can actually accomplish it.
So how much longer?
Well, that
depends on the model, obviously, right? So
depends on the model and use cases and networking and computation environment. But I can give you some rough ideas. Like right now, we are absolutely training AI models over multiple distributed encrypted databases. And again, it's slower than plaintext, obviously. And plaintext means just regular data, data that is not encrypted. But it's possible. Like very recently, we finished a project for fraud detection and anti-money laundering. And we were able to train a useful model in 4 minutes. So now we can say that, yes, I mean, if I was able to train it over plain text data, it would have probably taken like less than a minute.
Right.
That's fine. But like a minute to 4 minutes, that's not the real challenge. Like bringing multiple banks together and pushing them to share data, that's the real challenge.
And as a rule of thumb, when you get to inference, what's the difference between plain text and SMPC?
For inference, again, because we are using interactive protocols, like it's very different than doing inference over a single machine. So when you do inference on a single machine, it's really not about communication. It's just about computation and what kind of tools you are using to execute the computation. For us, because you need to do some back and forths between the model owner and the input owner, the network latency becomes really important. But we can right now we can do inference on medical images sub-second, so it's not limiting the deployment. We obviously we can improve it. We are improving it, but it's already within a range that is acceptable. Like that's not. We don't think that's the challenge. We think that the challenge is making people aware of the technology, which hopefully we are doing it in this podcast, and getting people excited to give it a try and really get a sense that this is real. It works.
And actually, that's a good example there, because medical images, that's computer vision, so those are, you know, as far as inference, those are good kind of things to benchmark. And if you can do that in a second, you know, that's pretty good.
Yeah, I mean, we need to kind of like, similar to any new technology, our job is to kind of like manage expectations. So for example, if you're training the state of the art, I don't know, like NLP model or some like huge model that Google's training, and it requires like 10,000 machines for like a few days to train it. Yes, maybe it's not a good idea to do it over encrypted data, but you kind of don't need to do it over encrypted data because Google already has all the data that Google has. But now we are focusing on, like, not every company is Google, right? They don't have the infrastructure, similar infrastructure. They don't have similar data sets. They don't have similar talent. So now the question is that oftentimes the talent and the data are in two different locations, or data is in multiple different locations. And now we come in as a glue or pipe, and we say we can connect these nodes. And now you can train a realistic machine learning model, good enough for your task, but you can do it for real. Like you are not bounded by all these kind of like legal and regulations that really limit you and kill the project altogether.
So, all right. So now I get to push back a little bit. So I have read some articles where the claim is, okay, so this homomorphic encryption and secure multi-party computation, they're great, but for now they're not practical for performance reasons. And the most practical approach is to use hardware, so secure enclaves. So what say you, CipherMode?
Right. We get that question a lot. It's a very fair question. It's a good question. We have a different opinion. We don't think hardware-based security is good enough and it's going to stay for long term. That's our current assessment. What we want to build is that we want to build a system where you can run arbitrary.
So wait. Let's parse that first statement.
Sure.
So why is using hardware enclaves not good enough? So I know the criticism is then you know, if there's a failure on the hardware side from Intel, AMD, or whoever, then you're vulnerable. But then on the other hand, Sadegh, that means the number of suppliers that need to get security correct is much more limited, right? So,
right. Let me break it down. So when you are using hardware to kind of like process encrypted data, I mean, technically it's not true.
It's not encrypted at that point.
Not encrypted. You are decrypting it within an environment which is claimed to be separated and isolated from other processes and OS itself. And now, how can you do something like that? So it's basically, many smart people have been thinking about this. They created a system, an architecture that allegedly does that, right? So it's basically a way of creating a castle where you say, okay, I'll put my most sensitive data within that castle and I try to make as good of a castle as possible. But it still is a castle. And as we have seen in the past, over the past few years, there have been many serious attacks on enclaves where you can actually extract data from within the enclave itself, which is not great. And when you think about why this is happening, is that every system is error prone. So how can you really shield the system from all types of generic attacks? It's very hard to do it. Whereas in our case, we are saying that yes, our systems are faulty too, but we're using crypto systems that provide formal security proofs. And just to even improve that, we open source CipherCore so that every person can scrutinize it and look at the source code. And we think that these are two different worlds. Like in one world, we have formal security proofs with mathematical guarantees, and people can look at the code. Yes, obviously there would be bugs, but we will look at it, everybody's looking at it, and then we solve it together. Whereas in the other case, it's out of the control. Like most of these systems are not even open source. They are closed source by some company. They have been being built. And like from time to time, some very smart computer scientist or computer architect would come along and says, okay, so now we can extract information this way. So there's kind of like an infinite game there. I agree that for many applications today, enclaves are faster compared to what we can offer. But I don't think we should build huge systems that for this short period of time, because as our technology is progressing, I think the end state would be a software-only solution with formal security proofs. There's no trick, there's no castle, there's no isolation. We just run everything that we want. And we can do it with anybody. So if you think about it, if you're using, for example, Intel enclaves like SGX, and someone else is using a different hardware, then you run into all kinds of compatibility issues, which is going to be devastating for long term. Whereas in our case, it's just a software, encrypts data, it's very clean, it's very homogeneous, and you can accomplish what you want to accomplish. So we think that there's a very big difference. In terms of performance overhead, I briefly mentioned it. Yes, there are many, many examples that you can test. Enclaves are faster than secure computation. But we think that's not the deal breaker. That's not the most important thing.
So to be clear, Sadegh, with enclaves, basically you're not really doing computation and encrypted data at that point. So
yeah,
it has to be fast, right?
It has to be fast, yes. So what happens is that you establish some connection with a certain part of the memory into another system, which is called enclave. And then essentially you have to decrypt data within that environment, run your computation, and then isolate it from the rest of the system. So that's actually how it's happening. There's no way to do computation over encrypted data in literal sense other than homomorphic encryption and secure multi-party computation.
So we've so far in our conversation we've talked a lot about models and machine learning and AI. So what about plain old analytics, SQL kind of BI kind of workloads? So those occupy a lot of interest inside companies as well, right? So
in
fact, even more at this point.
Even more, yes. And sometimes it's actually more aligned with our kind of like trade-off in terms of like performance versus usability versus accessibility. And we are definitely working on it. We actually have prototype systems. It's not, we are not offering it yet. It's in alpha version, but it's basically think of it as a system where you have a dashboard, a portal, and then you can start writing your SQL queries. And then you can specify what kind of databases you want to access. And without accessing those databases in plain text, and without those databases seeing your query, you can run your analysis. And then you get the insight that you want without looking at any data that you're not supposed to or you don't have access to. For sure, like any type of data analytics, BI, you can accomplish with CipherCore. You need one layer on top of it to make it more usable. And that's the layer that we're working on. So that you're not interacting with CipherCore, you just like write almost a standard SQL queries.
So there's another family of techniques that are not don't work with encrypted data that also get lumped in somehow. And here I'm talking about things like federated learning, differential privacy. And so can you, for our audience, kind of briefly describe how those techniques are used and why they're different? They address different problems.
Right, very good question. We come across many people where they think, okay, if you want to enhance the privacy during computation, then, okay, so there's like one set of tools, they all look similar, ranging from enclaves to homomorphic encryption to SMPC to federated learning. But actually, when you look deeper, the differences are pretty huge. They're like kind of like all put together as kind of like privacy enhancing technologies, but they almost have not so much in common. Sometimes they're competing with each other. Sometimes they're complementary. Sometimes they're just not relevant for that task. So just like briefly enumerate like all of these technologies, it ranges anywhere from differential privacy to federated learning, to SMPC, which we're using, to HE, to enclaves. And even we can stretch it to things like tokenization and anonymization. But to start from, let's start from differential privacy. So what does differential privacy provide? It basically, what is the main idea? The main idea is that you add a carefully tailored noise to your database to limit information leakage when you answer some query. Like, for example, when I have access to a database, which has like, let's say for simplicity, it has names and ages. That's it. So when I start asking questions like, what is the average of all the ages? Well, the answer is deterministic, but if you want to add the differential privacy layer, then you try to make it noisy. So it's not exactly the answer, but it's very close. And as you add more and more people, these noises start to cancel each other out, and then you get more accurate results.
But also it's not, the privacy guarantee is a knob that you turn, right? So
exactly. So there is one major knob, usually referred to as epsilon, and that knob is a trade-off between the accuracy of the result and the privacy guarantees that you can provide for individual records. And again, we personally do not.
So let me ask you this: so why? So at this point, based on what you've seen in heard in your conversation, so why do people use differential privacy if it's in fact doesn't guarantee privacy?
Very good question. I think there are a few reasons for it. One is that it's computationally very inexpensive. It's simpler to build and enforce. And it's a good way of, many people won't like this answer, but it's a good way of saying that we care about privacy without damaging the real underlying business. So it's basically, it's a trade-off. So you need to be careful like what you get out of it. For many of these real-world deployments of differential privacy, when you look at the real value of epsilon, it's something that doesn't really give you any sort of like privacy guarantees. So it's mostly a PR move, not really.
And to be fair, it's also usually a technique that's used in conjunction with other techniques. For
yes,
example,
that's a different story.
For example, differential privacy and federated learning get used a lot together, right?
Yes, you can actually, I can just like mention a scenario where SMPC, federated learning, and differential privacy kind of have to be used all together. It's not even like, if you want the best system, you have to use all three. And the example is the following. So let's say you have many distributed data sets. Let's say you have like more than 2. And now you want to train one AI model that uses all 3 databases. But at the same time, you want to minimize information leakage. So let's just start by using SMPC. So with CiperCore, yes, you can specify a training algorithm. Yes, you run it over encrypted data. There's no information leakage. But 2 things. One is that what is the performance? Number 2 is that what can you learn from the model itself about the original data? So kind of like mother inversion, or kind of like all kinds of attacks like membership inference attacks, that you try to learn something by just having access to the parameters itself, not to the training data, but just to the parameters. And then what can you do? Well, you can use differential privacy within SMPC, that before disclosing the final model, you add a carefully tailored noise that perturbs like the exact weights, but the model is behaving overall pretty good. And why would you use federated learning in this example? Because you can reduce a lot of computational overhead by doing some of these tasks locally and bringing some version of the model to data and doing that computation over plain text data, and then aggregate the updates using a secure method like secure multivariate computation. So in this example, which is a very real example, you have to use all three if you want to come up with the best system possible. If you choose any one or even 2 out of 3, it's suboptimal.
So listeners may think that our discussions are mostly cloud centric, right? So, but as you know, more and more models are getting deployed to the edge, right? So, in fact, on the mobile phone, for example, there might be models. So the stuff that you folks are building, are they cloud specific, or do you envision a day when some of these things could be used in models at the edge?
It's a good question. I think what we are doing is a little bit by definition different than edge computing. So in edge computing, you're focusing on minimizing communication, you're focusing on running things locally. And if you want to do that, you need to have access to all the information that you need. So if you want to do inference, you need to have some version of the model, you need to have your own input, you run it, you get to the outcome. Whereas in our case, by definition, we are talking about like collaboration, we are talking about multiple parties, we are talking about distributed things. So I think it's a bit different, but that being said, we are not cloud specific. We are actually, the system is built in a very cloud agnostic way. We didn't want to use any built-in features or built-in optimization.
Oh, yeah, right.
So basically you can have people on GCP, Azure, AWS, all working together using CipherMode, and they do not need to, none of them need to migrate.
Or so maybe, and also when you have devices on the edge like cars or phones and things like that, maybe that's where the federated learning aspect comes into play in conjunction with SMPC, right?
That's a very good example, yes. So for example, you can use federated learning on, let's say, Android devices or iPhones, and now you can use secure computation to aggregate those updates. And what this means is that you are not allowing a central server, let's say Google or Apple, to see the updates. You can just come up with an updated model without having access to individual updates, which I think is a very good improvement.
So here's another challenging question for you, right? So you mentioned model inversion. And one of my pet peeves in the space of adversarial ML is you've got all of these things, model poisoning, model inversion. But then when I ask people, so can you give me specific examples where things like this have happened in the real world? And people really struggle to give examples because a lot of the stuff is academic papers, right? So in your case, when you're talking about SMPC for ML and AI, is this a real need that you're seeing, or is this still kind of R&D? I mean, are people really dying for this kind of technology?
Yeah, it's a good question. I think we see more need on the training side. So it's basically not disclosing our training data. That's a major concern.
Not disclosing our training data to our competitors or within the company itself?
Both within the company and also to partners or competitors. So basically, like back to fraud detection example, it's in the benefit of all banks to collaborate to find more fraud. The reason that it's not happening is that nobody is willing to disclose their data to any other bank. So that's why it's not happening. So it's basically a way of removing that bottleneck, which usually comes from risks, regulations, privacy, and security. So it's basically, it's a major force. But when it comes to these kind of like attacks, like model inversion, membership inference, I don't think they're made up problems. I think we would see more and more as we're deploying more models for different kinds of tasks, and as we are spending more money per model. So
but on the data encryption and data privacy, that's real, right? Because that's basically now. Cybersecurity is essentially data security, because what do people do? They attack and they grab data, right?
Yeah, I mean, when you are collaborating with some other company, like what kind of guarantees can you have in the absence of secure computation? It's some legal contract, you're sharing data, you're hoping for the best. I mean, what can you do? Like, it's basically at the end, if you're not using secure computation, either you need to disclose your data or the other party needs to disclose your data.
Or I guess if you look forward to the future when this technology is so mature and capable, at least on the training side, you can imagine even companies themselves never have access to plain text. They just encrypt everything all the time, right? So
that's the end state, exactly.
Right. So then they get attacked. The attacker just gets encrypted data.
Exactly. We think that's how everything should take place, like eventually. Like at some point, you don't really need plain text data. I mean, everybody needs insights, everybody needs models. And what we are doing as a mission of the company is that we are removing this middle step. So instead of like, you have distributed data sets, you need to aggregate them, and then you need to do your thing, which is like analytics or training. We're removing the middle step. So we were saying that everybody would remain the sole owner of their data, but you get to the insight. So it's not like we're shutting down businesses, we are shutting down innovation. It's actually a catalyzer. It basically go from a state 1 to a state 3, and you don't need the state 2. We are using a state 2 because we didn't have good technology. It's just like the only way that we knew how to do things. But now we are getting closer and closer to like a real enterprise product where companies can use it internally, because obviously if you have like 100,000 employees, it's almost like a small country, or a small city. So you need to have some very restrict data governance, which right now, as of today, it limits innovation, it limits access, it limits projects. It doesn't have to be that way. Like data scientists do not want to like see individual records. That's not the interesting part. The interesting part is that you create better model.
So I'm releasing this. This podcast will air in the first half of September. So you mentioned earlier, in a few months, this PyTorch TensorFlow integration will be available. So put that in context. So like, what part of the year are we talking about? Is it early next year, early 2023, or towards the end of 2022?
I think it's right now, our timeline is close to end of 2022 for the first version. But that version will give you the ability to like describe models in Keras. If people have started using like secure computation today and they have played around with some of these secure computation libraries, I don't think they had a very good experience. It's basically, you need to know a lot, both on the cryptography side and about the specifics about the library in order to be able to use it. But with CiperCore, you can look at our examples. You can literally like just like write almost regular looking code. And then all the translations to protocols and execution and making sure that what kind of secrets are exchanged, that's all taken care of by CiperCore.
So as we close here, Sadegh, so what in the research world has caught your attention that you think people should start paying attention to now? So by research world, I mean, since you're much more steeper, for example, in security than me or our audience. So is there anything in that world that you think is still somewhat under the radar?
Well, I think it's still the entire field of secure computation is a little bit not really understood by many people, like the power behind the technology. And if you think about like 5 years ago, the performance overhead of secure computation was so large that you couldn't do anything in practice. To give you some like little bit of benchmark, if you wanted to do inference, some of these early protocols, they require like 300 seconds for one MNIST inference.
Right.
300 seconds. So obviously that's not going to be used. But right now we are talking about like milliseconds. Obviously it's much larger than plain text, but we think that it's very...
This is SMPC, right?
Yes, SMPC, yes. Yeah. So we are basically, I think we are moving to like a new phase. The phase is that we can capture a good percentage of all applications that can be done with secure computation. It's not 100%, it's not 50%, but it's a very significant percentage.
So what has been the reaction to the open source project CipherCore? I imagine there's people who were surprised.
Yes,
by it,
yeah.
right?
Especially we kind of like open sourced it almost 1 year after we established the company. So it was in a very, relatively speaking, short period of time compared to how big the challenge was. And it's kind of like the first real open source library to be able to support generic computation. So right now, since we open source it, we actually we have seen that it has been downloaded more than 10,000 times, which I think is a pretty good number for a new and niche technology. And 15 big companies have reached out to us, and they start asking questions like, can you support X? Can you add Y? When can you have feature Z? So it's a very real conversation. And I think the most positive side of this is that they understand that there's a solution for their problem. Now, the next step is that, yes, the product is not complete. Yes, we need to add features, but that can be done. Whereas the awareness part, if you have never heard of secure computation, it's a very, very counterintuitive concept. Like either you would think that either you're protecting data, which obviously you can using traditional cryptography, or you're not protecting it and you can use it, which is just like regular execution. How can you have the best of both worlds? Like it's kind of like counterintuitive. How can you protect data while using it?
And by the way, we've talked about this privately in the past, but the product itself and even moving forward, the open source project is architected in a way that hey, if in the future a new unknown technique emerges, then your code will still work because CipherCore will have an intermediate representation layer that abstracts away a lot of the heavy lifting, right?
Exactly. Like right now, there's only one file, literally one file that is dependent on the exact protocol. So if tomorrow you want to change that, it's a very, very easy step to do it. Whereas like many of these academic projects, they're really tied to that protocol. And since day one, we thought that, yes, this might be the best protocol today, but tomorrow, I mean, the smart people can come up with better protocols. So we need to have a way of supporting protocols, but in a very short period of time. And I think that's what we deliver.
So will CipherCore still protect me after quantum computing in the post-quantum encryption world?
Yes. So it's a very good question. There was this recent news by NIST that they selected 4 proposals for post-quantum cryptography. And what is interesting is that the entire crypto system that we're using is and can be post-quantum secure. So again, going back to long-term support.
What about performance?
No, almost same performance. Yes. So it's not going to drastically change things. It's basically just like you flip a switch and then maybe it's like 10% slower, but I mean, it's post-quantum secure. So there's nothing fundamental within our platform where would be broken by quantum computers.
And with that, thank you, Sadegh.
Thank you, Ben, for having me.